Okay, in continuation with our discussion on flux force relationship, we come to page number 3. So the fluxes and forces in the expression of S prod dot, what we have written already, are related to each other. Experimentally, the relation is often linear. That means the flux varies linearly with that of force. That means the power on flux and force both are 1. So for example, Fourier's law of heat conduction says that the flux of energy and as heat is directly proportional to the temperature difference. That is, Ju is proportional to T2 minus T1. On the other hand, T2 minus T1 is proportional to 2 minus T1 by T1 T2. That is, T2 minus T1 equal to 1 by T1 minus 1 by T2. That means T2 minus T1 is proportional to Xu. So we get Ju is proportional to Xu. Similarly, Fick's law of isothermal diffusion says that the flux of matter is directly proportional to the difference in concentration. That is, Jn, flux of matter, is proportional to concentration difference. That is C2 minus C1. Once again, C2 is logarithmically proportional to mu2, the chemical potential, and C1 that with the chemical potential of component 1. So Jn is proportional to mu2 minus mu1 at constant temperature, because we have taken the isothermal condition. Perhaps a more familiar than Fourier's law or Fick's law is the Ohm's law, which says that an electric current I is directly proportional to a voltage difference V2 minus V1. So I equal to V2 minus V1. Once again, this V2 minus V1 is the force of electrical conduction. So I, the electricity conducted, is proportional to the force of electrical conduction, and the power on this and this is just 1, so that is directly proportional. So they are linear, the relationship is linear. So as a whole, the point is that Ji is proportional to Xi. Okay, so for I in general is in all these three cases, that is, the flux is linearly proportional to the force. So we are in the linear flux force regime. So now let us come to the next page, that is page number 4. So it can be said that in general Ju is proportional to Xu, or Ju is A into Xu and Jn equal to B into Xn, where A and B are the proportionality constants. In this analysis, chemical flux force relations are used, that is the Fourier's law, Fick's law, or Ohm's law, where there is a difference in only one quantity, that is either temperature or concentration or chemical potential or voltage respectively. However, the expression for S prod dot, we have two fluxes and two forces, where X prod dot equal to Ju Xu plus Jn Xn greater than 0. Is not that simple, because here two fluxes and forces, not like Fick's law or Fourier's law or Ohm's law, where there is only one flux and one force. Here we have two fluxes and two forces. So we have more than one quantity is being varied. In general, it turns out that experimentally Ju equal to, so instead of the constant AB, we write LUU as one coefficient. So Ju equal to LUU plus XU plus LUN plus Xn, because the flux of energy is not only connected with the force of energy but also the flux of the force of matter, because when the matter flows, it also takes some energy, it also takes heat. Similarly, Jn, the flux of matter, is Lnu into Xu plus Lnn into Xn. So these four quantities are the proportionality constants, and these proportionality constants are written as LUU, LUN, LNU and LNN are termed as phenomenological coefficients. So in non-equilibrium thermodynamics, these proportionality constants, they have a special name. They are named as phenomenological coefficients. So this term phenomenological coefficient is very important. So you must note it. So which are to be determined experimentally. They need to be determined experimentally. So the physical significance of the diagonal phenomenological coefficients, that means the coefficient which connects a flux with its own force. So these LUU and LNN, they are the diagonal phenomenological coefficients, and LUN and LNU, they are off diagonal phenomenological coefficients, because this thing connects XU with JU. Once again, this thing connects XN with JN. So they are the flux which is, they are the phenomenological coefficient which connects a flux with its own force, and these are off diagonal phenomenological coefficients. They connect a flask with some other force. Okay, so be careful about the term diagonal phenomenological coefficient and off diagonal phenomenological coefficients. So the physical significance of the diagonal phenomenological coefficients LUU and LNN are such that they connect a flux with its own force, which are designed in such a way that LUU and LNN are always positive. So we can algebraically prove that LUU and LNN, they are positive. Okay, so that will be done in somewhere in next class. On the other hand, the off diagonal phenomenological coefficients, that is LUN and LNU, are the cross coefficients and relate a flux with another force. And these off diagonal coefficients, phenomenological coefficients, they can be positive, negative, or even zero. So the diagonal phenomenological coefficients, they are always positive, and the off diagonal phenomenological coefficients, they can have any value. They can be negative, positive, or zero. So now we come to the last page of this part of the discussion, that is page number 5. So the physical significance of the coupling term may be a little difficult to visualize, since still a nice example can be set by the isothermal diffusion of a solution of sucrose in water. So suppose a sucrose solution where sucrose is concentrated, it's being diffused in pure water. So you take a sucrose solution in test tube and just take water in a beaker and put the sucrose solution into the beaker. So then naturally, according to the Fick's law of diffusion, the sucrose will gradually mix with the water and a homogeneous solution will be prepared. So the Fick's law says that there will be a flux of water as a result of the difference of chemical potential of water from one region to another, and there will be a flux of sucrose as a result of difference in the chemical potential of sucrose. So when sucrose is moving inside water, same time water will move inside sucrose solution, because there is a chemical potential difference of water in the bulk water and within the sucrose solution, and chemical potential difference of sucrose within bulk water where the sucrose concentration is initially 0, and that in the sucrose solution. So that means the water will diffuse inside sucrose solution and sucrose will diffuse inside water solution simultaneously. So the sucrose molecules are partially hydrated, so the flux of sucrose molecules also partially contribute to the flux of water, because when sucrose goes, it takes some water along with it. Thus, there is a flux of water molecule as a result of chemical potential difference in sucrose, in addition to the flux of water molecule as a result of chemical potential difference of water. The flux force relation describing this phenomena, that is the flux of water JW equal to LWW into XW, that is the force of water, that is the chemical potential difference of water. And then also sucrose is partially hydrated, so it will take also water, so the force of sucrose will also contribute to the flux of water, and this will be connected by this off diagonal phenomenological coefficient. So where JW is the flux of water and XW is the chemical potential difference of water and XS is the chemical potential difference of sucrose. Similarly, the flux of sucrose can be written as, on the other hand, the similar thing will happen in case of sucrose, and Js will be equal to LSW XW plus LSS into XS. So if the water molecule and sucrose molecule are diffused completely independently, suppose if it so happens that water molecule doesn't depend upon sucrose concentration and diffusion of water molecule, and sucrose diffusion doesn't depend upon water, then what will be? The cross coupling coefficients will be 0. So in that case, this thing and this thing will be 0. But as this JW is partially dependent on the force of sucrose and also the Js is partially dependent on force of water, so these cross coupling coefficients will be non-zero. Had it's not dependent on this, not dependent on that, then these two off diagonal coefficients would have been 0. So we can say that in the whole discussion, our flux force relationship, what we get, J and X, they are connected in such a way that the power on Js is 1. So everywhere the power is 1. So the flux is linearly dependent on the forces. So we are in the linear flux force regime. So whatever now onwards the discussion will make, where the fluxes will be linearly dependent on forces. So we will stick to the part of the non-equilibrium thermodynamics where the flux force relationship are linear. Okay. So with this we end the part of discussion what we started yesterday, and once you understand this part, we'll proceed further. Thank you very much.